Hello everybody and welcome to another explanation video. Today, I'm going to be talking about divisibility rules. So, this document, basically, this presentation is going to be telling you how to tell if a number is divisible by another number without needing to do any division. So, you will need to know multiplication, subtraction, and addition, but you don't need to do any division, because in my personal opinion, division is the hardest of all the basic arithmetic. Um, I mean, it's not super duper hard by any means, but I think it's out of multiplication, subtraction, addition, division, in my opinion, I believe is the hardest. And especially when you get into the really large numbers, I think it'll be pretty handy to not have to know just off the top of your head whether or not a number is divisible by another. Or at the very least, if you're using pen and paper and you're not using a calculator, then well, it's easier to tell if a number is divisible by or not. Now, I'll immediately clarify that this video is more just a thought experiment of sorts, and more just to kind of get your math brain going. Is this really super practical? Not particularly. No, you're not going to really use it in your everyday life, but maybe you'll come across a situation where you're like, I remembered this video, and now I can know. So yeah, let's get right into it. Oh, and you might be wondering, right? Why does it say improved? It's because there's another video already called Divisibility Rules, which I'll explain right here. So yeah, video is basically kind of a sort of a continuation of a video by Ding called Divisibility Rules. The link is here. That's more for me because I don't expect you guys to type out the link. But yeah, I have it there for my own reference. And yeah, let me clarify immediately though. Not only is watching the original video not necessary, it's probably not recommended actually, because it'll confuse you, okay? Of course, for the sake of transparency, I want to clarify that this video has a lot of influence and inspiration from the original video, but I don't actually think you should watch the original video if you haven't already. In fact, I think you should watch this video first, and the reason why is because the way that Michael in the video does it is a different method than what I'm going to do, and it might confuse you. It might actually legitimately confuse you if you watch that video first and then watch mine. So, yeah. Also, the original video only showed divisibility from 1 to 9, but I will, however, be going all the way up to 20, kind of more in depth going up to 20. I'll actually be going all the way up to 50. But in terms of going super in depth, only all the way up to 20. So yeah, and I'll also add my own twist, and I'm not going to be using the same methods, all of the same methods. Some of the same methods I will be using, but not all of the same methods. I came up with my own methods and stuff that I think is super interesting. I'm very excited to share this with you. So, what is divisibility? Well, if a number is divisible by another number, it simply means that that number can be divided into that other number evenly, aka without leaving any remainder. So 4 divided by 4, that means that it is divisible. 4 is divisible by 4 because when you divide it, it's 1. Is 4 divisible by 1? No, it leaves a decimal. Is 4 divisible by 5? No, it leaves a decimal. So that is what divisibility is. I'm assuming you already know this, but it's good to kind of explain everything. All right, so I want to reduce redundancy here. This is important, okay? So all future mentions of the word number mean integer. If I'm referring to a non-integer number, I will specify that. Otherwise, just assume that anytime I'm talking about a number, I mean an integer. Also, when I say first digit or final digit, I'm obviously referring to the actual digits that you see when you're writing it out. I'm not adding any potential invisible digits after that, right? Like, if I say like 25, right? When I say the first digit, I'm obviously referring to the 2 and not any number of invisible zeros you could add in front of it. And when I say the final digit, I'm obviously referring to the 5 and not the decimal point and any number of invisible zeros you could add after it. I'm obviously referring to just the digits that are on there that you can see. That should be obvious, but there's going to be some people that might think that they'd be confused by that, so immediately clarifying that. So, to start off with, we're going to talk about the format because there's going to be a lot of showcasing the format. So, the format, the very basic format that you're going to see is that you have the input number, then the division sign, and then the number that you want to know if it is divisible by. And the division sign will be replaced with the slash sign sometimes. Actually, I do show the division sign quite often, but sometimes you'll see it as a slash. I'm assuming you know both mean divisibility. So, yeah, you're gonna see some letters here, like CBA or DCBA or FEDCBA. Now, what does that mean? Well, it simply is meant to represent the digits. They are not multiples. So, if you see CBA equals 412, that means that C equals 4, B equals 1, and A equals 2, okay? Well, like I said, these letters are not meant to be multiplied together. It does not mean C times B times A. These are just placeholders for the numbers. And it's important to know that because I'm going to be combining numbers and letters together. For example, 10A and 5B. 10A does mean A times 10. 5B does mean B times 5, okay? But CB, right? That does not mean C times B. That just means the letter C and then the letter B that could represent any two-digit number theoretically. Well, I guess if it's a two-digit number, it would be B and A, but you get the idea. Uh, and also, if you did happen to watch the original video, either because you didn't listen to me or you've already watched it, um, I am putting it backwards, right? I'm not doing ABC. I'm doing CBA. And the reason why is because I'm going to be doing numbers that are larger than 100. And because I'm doing numbers that are larger than 100, that leaves a really awkward situation where what do I do to represent larger numbers than that, right? If I wanted to extend the alphabet in the same direction, let's say I make A, B, C, D, E, right? For like a 10,000, a number all the way up to the 10,000th digit, all of a sudden, A went from representing the hundreds place to representing the 10,000th place. And I don't want to deal with any of that. So I'm going to be doing it what I consider to be the logical way and putting it in reverse alphabetical order. And again, the reason why is because that way each number or each letter consistently is representative of the same power of 10. A will always be 10 to the power of 0. B will always be 10 to the power of 1. C will always be 10 to the power of 2, and so on. Um, and I think I can kind of explain that right here, right? A, B, C. That was the original video, right? Where A times 100 plus B times 10 plus C times 1. But that's not what I'm doing. I'm doing it backwards for the sake of consistency, because otherwise, if I did it his original way, again, I would either have to change the value of A or B or C every single, with depending on how large the number is, or I would have to go backwards in the alphabet, which is actually what I originally did. I just kept the ABC, but if a number was 1000, for example, then I would go backwards and it would start with a Z, and it would be ZABC. And before that, I would have a Y, so it would be YZABC. And that was very confusing, so instead I just went with reverse alphabetical order. So yeah, I will show the proof at the top using the logic from the original video, then show an example below it, and if there is a cycle for the divisors, I will also show that. So I say let's get to it, but I think, yeah, there's one more slide here. We're going to start off with our first category of numbers, and these are numbers that are divisible by any power of 10. This is significant because if a number is divisible by a power of 10, that means that there's eventually a breakoff point where you don't need to know what the numbers are ahead of that. So probably the easiest example is even numbers, right? If a number is divisible by 2, you don't need to know how big the number is. You don't need to know any of the digits in front of it. The only thing you need to know is the final digit and if it is an even number. You don't need to know any of the rest of it. It could be 42 or it could be 756,242. It doesn't matter as long as you know the final digit. So that applies to all of these numbers in this first category, which are numbers that are divisible by any power of 10. So first example is 1. Pretty straightforward. I don't think I really need to explain it. Every number is divisible by 1 as long as the final digit is 1, 2, 3, 4, 5, 6, 7, 8, or 9, or 0. It's divisible by 1. Literally every integer is divisible by 1. In fact, that is the definition of being an integer. So don't think I need to explain it any further. Divisibility by 2. This is the same thing as being even. As long as the final digit is either 2, 4, 6, 8, or 0, then the number is divisible by 2. 42 It's divisible by 2 because it gives us 21, and 21 is an integer and not a decimal point. Again, this is so simple, I don't think I need to explain it. Divisibility by 5, also very straightforward, very simple. If the number in the singles digit is either 0 or 5, it's divisible by 5. 30, it's divisible by 5. 110, it's divisible by 5. As long as the final digit is either 0 or 5, it's divisible by 5. Similar logic here with 10. If the final digit is specifically 0 and nothing else, that means it's divisible by 10. So, and also every number that's divisible by 10 is also divisible by 5 by definition. So 50 is divisible by 10. 120 divisible by 10. Next up is 20. So now we actually have to look at the final two digits, not just the final digit. So if the final two digits are either 20, 40, 60, 80, or 0, both 0, then the number is divisible by 20. So, could be 120, 240, 460, 880. As long as the final two digits are either 20, 40, 60, 80, or 0, then the number is divisible by 20. So any number divisible by 20 is also divisible by both 10, 5, 4, and 2. I say both, but that's more than 2. But, So 620 is divisible by 20. Last two digits are 20, so obviously it is divisible by 20. Excuse me. 25. How do we know if a number is divisible by 25? If the final two digits are either 25, 50, 75, or 0. This is supposed to say 0, two zeros. I put 100 just because I wasn't really thinking, I guess. But really, this should be 25, 50, 75, or 0, 0. So if the final two digits are any of those, then that means that the number is divisible by 25. And also any number divisible by 25 is also divisible by 5. And last but not least for this category, because again, I'm only going up to 50. Again, this theoretically continues forever as there are an infinite amount of numbers that you could calculate the divisibility for, but I'm going to go only to 50, and how do we know if a number is divisible by 50? If the final two digits are either 50 or 00. Straightforward. Any number divisible by 50, also divisible by 25, 10, 5, and 2. And of course, again, some of these numbers are also divisible by 4, but not all of them. And yeah, 600 divided by 50 is 3, for example, because the last two digits are 0, last two digits are 0, so you know that it is divisible by 50. Alrighty. So, now I need to explain something. So for the rest of this document, I actually have to prove why it works, because it won't be immediately obvious, right? So far in this document, I've gone with ideas and shown you stuff that's like so obvious that I don't need to explain anything. But now we're getting into the kind of part where I need to actually prove why it works. So remember how I said that EDCBA, any length of integers, right, is A times 1 plus B times 10 plus C times 100 plus D times 1,000 plus E times 10,000, continue on forever, right? Well, we can take this fact about the way that we display numbers with base 10, and we can actually take out some numbers and still be accurate. But we can prove that if part of a number, or part of the equation, is divisible by a certain number, then the whole equation is divisible by it. This is actually probably where the benefit of watching the original video by Michael probably comes in handy. And also, by the way, I referenced that original video. At the time I was making this document, that was really the only video I knew about. Since then, a video by Stand Up Maths and another video by Wrath of Math have kind of talked about this to a certain extent, but at the time I made this document, those didn't exist, so yeah, I decided not to add or change anything, but either way, let me show you what I mean by this. So let's say that we have a 5-digit number and we were trying to prove whether or not any number EDCBA is divisible by 5. But let's try and do it in a complicated way. We're going to specifically do it in a complicated way so that you can kind of understand what we're going to be doing later, okay? That's the purpose. So, as I said, EDCBA is a times 1 plus b times 10, and so on. But we can take out numbers that fit our divisibility, and then we can split it into two different categories, okay? So we can rewrite this entire thing as a times 1 plus b times 5 plus c times 5 plus d times 5 plus e times 5 as one bracket, and then split it apart and add into a second bracket b times 5 plus c times 95 plus d times 995 plus e times 995. Now you might be wondering, what's the purpose of doing this? But as you can see here in the parentheses, all of these numbers have to be divisible by 5. These numbers here, well, I mean, we have most of it here has to be divisible by 5, but this theoretically might not be divisible by 5. And that's kind of where the proof comes in, right? We have to prove that A is divisible by 5. But we know, again, using our logic here, that this right here has to be divisible by 5, which again, is kind of redundant because all of this already is divisible by 5, right? The 10 and the 100 and 1000 are all already divisible by 5, and these are already all divisible by 5. But again, the purpose is to take it out so I can show you, okay? The purpose is to show you an example. So the sum in the brackets added together with the sum in the parentheses is the same as the original, right? So b times 5 plus b times 5 is b times 10. C times 5 plus c times 95 is c times 100. So that's the purpose, so that you understand the idea of us separating it out so that we can get numbers in a parentheses that are all divisible by one number, and then have another number that are all added up together in brackets that we have to prove their divisibility for. And I kind of already say that. I'm not going to reread this. You can read it if you want, but I kind of basically just said that. So yeah, this is because a number that is divisible by n plus any other number that is divisible by n will itself be divisible by n. So if I add, let's say for example, if I am adding 5 plus any number that is divisible by 5, that means that that sum has to also be divisible by 5, because that a number that you're adding to it is also divisible by 5. So 5 times 20, or 5 plus 25, for example. 25 is divisible by 5, so that means that 5 plus 25 is divisible by 5. So just so you understand, right? Now again, this is obviously a complicated way of doing it, but the purpose is to show you, so you'll be less confused later on. So, with our first example, we have our first proof, which is divisibility by 4. How do we prove divisibility by 4? All we need to do is prove that A plus 2B is divisible by 4. So, I get to show you this actual example right here, right? CBA equals A times 1 plus B times 10 plus C times 100, right? So, B times 10, not divisible by 4. A times 1, not divisible by 4. C times 100 is divisible by 4, and every number after that, every iterative power of 10 after that is also divisible by 4. So, we can take out here, look at this, right? We can take out 2b, and we can take out 0, 100, because we don't need to, and we can take out 1a, so now we're left with a times 1 plus b times 2 plus c times 0, and then that's in our brackets, and then add that with the parentheses of a times 0, because we already have the a, b times 8, and c times 100. So altogether, this equals the same thing. These are the same thing, because b times 2 plus b times 8 equal b times 10. But the benefit of this is that this right here, this stuff in the parentheses, is divisible by 4, because it's 8 and 100, which we know are already numbers that are divisible by 4. So all we need to do is prove that a times 1 plus b times 2 is divisible by 4, and if this is divisible by 4, and you're adding it to a number that is also divisible by 4, then the whole thing has to be divisible by 4. So yeah, that's basically, I think what I wrote down here is basically what I'm going to say. Let me reread it real quick, because I was saying that off the top of my head, not reading. Not only that, no matter how large the number is, no matter how many digits we add in front, we only need to know the final two digits. All we need to do is know if A times 1 plus B times 2 is divisible by 4, because any number after that doesn't matter, because the power of 10 is divisible, or the power of 10 past 100 is also always going to be divisible by 4. So yeah, since there is a continuous cycle divisibility at 100, we only need to know if at least the last two digits are divisible by 4, and the whole number will be. So that's basically what I said. So that was a kind of a showcase, but now let's show an actual proper example. And let's take the number 184. Is the number 184 divisible by 4? Let's see. A is our final digit here. Wait, this is wrong. This is the wrong. This is supposed to be the other way around. Excuse me real quick while I fix this. A is supposed to be it's still 0. No, it's not 0 times A. It's 1 times A, which is 4. This is the same. So this is going to be 4. I just got my numbers mixed up, so sorry about that. There I go. And this is going to be in reverse order. So 4 plus 16 plus 0. So yeah, there we go. Okay, so sorry about that. I wrote it down in the wrong order and only noticed now. So we have the number 184. Well, let's go through, and we have A, which is the final digit here. We're going to see if A times 1 is 4. So we're going to not jot down this 4. We're going to keep it down here. And then we have 8 as our second digit, so we're going to multiply 8 by 2, and that's going to give us 16, and that's going to be our second sum, part of the sum. And if we want to, we can keep going after that, 0 times whatever. We don't have to. I just do it to kind of be thorough, but we only need the final two digits. And that'll leave us with 4 plus 16 plus 0 equals 20. And since 20 is divisible by 4, we know that 184 is also divisible by 4. So, yeah, and another note, very important, for these divisibilities, for any number that is divisible by any power of 10, if the sum you get is 0, that also works. So, this isn't going to be the case later on. I want to clarify that, right? This isn't going to be the case later on. But for these numbers that are divisible by a power of 10, let's say if you got the sum together and it equals 0, that means it's also divisible by 4, or divisible by whatever you're showing. So, for example, if you were to take the number 100, right, that would be 0 plus 0 plus 0, which equals 0. But that's fine because these are categorized under divisible by a power of 10, and thus we're going to say that 0 is divisible by 4. So I want to immediately clarify that, because there are going to be some instances later on where that is not the case. And if you get a 0, that means you did something wrong or it's not divisible. So that's 4. Let's move on to... Oh, yeah. So now you understand it. You get the idea. I've given a thorough rundown of an example, so I'm not going to explain in detail. I'm not gonna explain in detail the intricacies that have already been explained. You get the idea. So we're gonna basically make it look a lot more like a stat sheet. And we're also gonna remove the multiplication symbol. So a times 10 will be rewritten as 10a, and a times 1 will just be a. So again, the purpose is, you kind of get the idea now. We're gonna make it a little bit more simplified and kind of go through the characters again. This page, I don't know if I said this in this recording or if it was in the previous recording, which I deleted, but this document is 70 slides long. I don't want to be here all day intricately explaining everything once you get the general idea. The only exception here as well is 0a. We're going to keep 0a. If something is 0 times a, we're not going to delete it. It is 0, of course. It doesn't have any value, but for the purposes of showcasing it to you guys and showing you that A, I didn't forget it, and B, it's important to keep track of what multiples we have. If something is multiplied by 0, we're going to keep it in the representation. If you're doing it yourself, of course, you don't have to, but it's for the purposes of showing you guys. So, DCBA, so this is a number in the thousands, right? Where D is 1,000, whatever. So divisibility by 8. What are the multiples of 8? Kind of have them right here. So we have 16, 24, 32, 40, 48, 56, 64, 72. Okay? It's important to keep track of the multiples, but not 100% important. Well, it's important when we do the math at the bottom when we figure out whether or not a number is divisible or not. So, how do we prove divisibility by 4? It's by using the formula a plus 2b plus 4c. So if you add a together plus 2b plus 4c, and if this number is divisible by 8, then your entire number is divisible by 8. So why do we know this? Well, here's the proof. We have a plus 10b plus 100c plus 1000d, and then we can separate that into a plus 2b plus 4c plus 0d. So this is what we have to prove. And 0a plus 8b plus 96c plus 1000d. This number here is divisible by 8. 8 is divisible by 8, obviously. 96 is divisible by 8, obviously. So all we need to do is figure out if 4 times this number here plus 2 times this number here, or this digit here, plus a is divisible by 8. So here's our example, 3,640. So 1 times a equals 0, 2 times b equals 8, we're going to jot that down, 4 times 6 equals 24, we're going to jot that down, and 0 times d is 0, of course. So 8 plus 24 equals 32. So obviously, you're going to have to keep track of the final 3 digits this time. Rather than just the final 2 digits, you're going to need to know the final 3 digits. And if 4 times the hundredths place plus 2 times the tens place plus the singles place is equal divisible by 8, then the whole number is divisible by 8 for the proof that I just showed up here. So next up, 16. This is actually going beyond the original video. At this point, we're going into, even if you watch the original video, this is uncharted territory. This is not in the original video. So the multiples of 16 are 16, 32, 48, 64, 80, 96, 112, 128, and so on. So how do we prove if a number is divisible by 16? Well, we have to do a plus 10b plus 4c plus 8d. Okay? So if a plus 10b plus 4c plus 8d is divisible by 16, then the entire number is divisible by 16. So again, here's the proof why. We're going to take out the a and the 10b because obviously 16 cannot possibly be divisible by 10 because duh. 100c, we're going to take out 4 here because 96 is divisible by 16. For 1000d, we're going to take out 8 because 992 is divisible by 16. And for 10,000e, we're going to leave it. We're not going to mess with it because 10,000 is already divisible by 16. So, great. Here's an example. 18,624. I don't know off the top of my head if it's not divisible by 16, and we can find out without having to do any math. Or without, sorry, God, we have to do math without having to do any division, is what I meant to say. So, 1 times a, which is 4, right? 4 plus 10 times b, 20. So we have 4 plus 20. 4 times c is 24, and c is 6 here, so 24. So we have 4 plus 20 plus 24. That is gonna, we're gonna jot that down here. Then we have 8 times 8. Again, we have 8d here, so 8 times 8 is 64. Keep the 64 here. And e times 0, because again, e is in the 10,000th place, so we don't need to keep track of it. So this all of a sudden is a lot easier to figure out if it's divisible by 16. This number, just by looking at it, I have no idea if it's divisible by 16. This, however, I know if it's divisible by 16, or at least I have a much better chance and much better ability to do so. So 4 plus 20 plus 24 plus 64 equals 112. And by the way, if you don't know if a number, once you do all the addition together, and if you don't know if the number is divisible by 16 or not, you can keep going with the process. So let's say, again, with 112, let's say you don't know if 112 is divisible by 16. Well, you can do 2 plus 10 times the singles digit, so this would be 2 plus 10 plus 4 times the hundreds digit, which is 400. So, sorry, not 400, 4, my bad, sorry. So it would be, I'm doing this off the top of my head, I'm not even looking. So we have 2 plus 10 plus 4 is 16 itself. 2 plus 10 plus 4 is 16 itself. So obviously 16 is divisible by 16. Bada bing, bada boom, you're good to go. So next up, we have 32. Now we're going to have to know all the way up to the 10,000th digit. So multiples of 32 are 32, 64, 96, 128, 160, 192. So A, this is the formula, A plus 10B plus 4C plus 8D plus 16E. Again, the proof is right here. 10B, 4C, 8D, 16E, and 0F, and that is because this is the smallest amount of numbers you can take out while still keeping it as a number that is divisible by 32. So in order to know if a number is divisible by 32, you're going to have to take 1A, 10B, and then we're going to remove 4 from C, we're going to remove 8 from D, giving us 992, and we're going to remove 16 from E, giving us 9,984. And then, again, 100,000, 1 million, all numbers beyond this point are, in fact, divisible by 32 by default, so we don't need to worry about that. So, our primary example, 284,480. The first digit is 0, 1 times A, 0, 10 times B, 80, 4 times 4, which is this digit here, 16, 8 times 4, which is 32, 16 times 8, which is 128, and there's nothing here. Oh, no, the 2 is for the F, but that doesn't matter, we don't need to know the F. We just multiply it by 0, so 0, and that leaves us with 0 plus 80 plus 16 plus 32 plus 128 plus 0 as well if you want to include it. I didn't. And that gives us 256. And 256 is, of course, divisible by 32. If you know anything about binary, you would know it is, in fact, divisible by 2. But again, even if we didn't, we could theoretically continue on, and we could do, like, 6 plus 50 plus 4. 6 plus 50 plus 4 is 60... Wait, is that right? Did I do that right? No, 6 plus 50 plus 8. My bad. This is 4 times 2. 6 plus 50 plus 8 is 64, and of course 64 is divisible very easily and noticeably divisible by 32. So that's it for all of the numbers that are divisible by power of 10. That was the easy stuff. So now we're getting into the numbers that are not divisible by any power of 10. This is new stuff, okay? We're getting into new territory here with new interesting methods that weren't even really discussed in any of the videos I watched, and I kind of came up with them myself. So any number that is divisible by any power of 10, of course, power of 10 being 10, 100, 1000, 10,000, etc. With these numbers, with numbers like these, rather than being able to look at only the final few digits, you unfortunately have to take into consideration every single digit. I say every single digit. I meant to say every single digit. You're going to have to literally take into consideration every single digit, as they will have an effect on divisibility. So, yeah, thankfully the first two examples are rather easy, but it gets very complicated very quickly, and you'll see why very soon. So, first off, divisibility by 3. For divisibility by 3, again, this continues on forever, but if the number, let's say a number is 1,000 digits, you would have to add all the digits together, and the sum of all digits is divisible by 3. Why is this the case? Well, let's remove 1A, 1B, 1C, 1D. Again, this is what we're going to calculate for, right? If all of this is divisible by 3, then the whole thing is divisible by 3. And we know this because this part right here, the 1 that we took away from it, taking away 1 from 10, taking away 1 from 100, and taking away 1 from 1,000, this gives us 9B plus 99C plus 999D, and this is obviously already divisible by 3. So all we need to do is find out if this part is divisible by 3, and the whole thing is divisible by 3. Here's a good example, 5,310. So, this is a 0 right here, so we're going to take a 0 plus 1 plus 5 plus 3. Why is it in this order? This is a weird order. C is 3. So this should be C3 equals 3, D5 equals 5. I apologize, I somehow didn't notice that mistake, but either way, 0 plus 1 plus 3 plus 5. 1 plus 3 plus 5 is, of course, 9, and 9 is obviously divisible by 3, so the whole number is divisible by 3. By the way, this means that you can rearrange the numbers basically however you want, and it's also going to be divisible by 3. So 5,310 divisible by 3. 5,301 also divisible by 3. 5,103 divisible by 3. It doesn't matter the order of the numbers because we're adding them all together, and as long as the entire thing equals a number that's divisible by 3, then you're good to go. Next up, very similarly, this one I'm sure that you definitely know. There's a high chance you knew the previous one, but for sure you know this one. And this is divisibility by 9. And if the sum of all digits is divisible by 9, then the entire number is divisible by 9. For the exact same reason as with divisibility by 3, 9b plus 99c plus 999d, obviously all these numbers are divisible by 9. So, 6, let's take the number 6,876. 6 plus 7 plus 8 plus 6, again, going in reverse order. 6 plus 7 plus 8 plus 6 is 27. 27 is obviously divisible by 3. And even if you didn't know, 2 plus 7 equals 9, obviously, that's probably where the majority of the thing comes from, right? You know that it's 27 is divisible by 9 because 2 plus 7 equals 9. 36 is divisible by 9 because you know that 3 plus 6 equals 9. 45, 54, 63, you get the idea. So, those were the easy ones. However, now we're going to get into something very, very interesting, which again, most certainly was not talked about in the original video. We have the dual multiples of the least common unique multiples. This is going to be really interesting. So for some numbers, the by far easiest way to know whether or not a number is divisible by another number is to check and see if it is divisible by at least 2 is what I was trying to say. It says by its it's sorry. If it's divisible by its least common unique multiples, meaning the multiples cannot be the same and one multiple cannot be a multiple of another multiple. So for example here, 12, both 6 and 2 are multiples, right? 2 times 6 is 12. However, they cannot be used for this method because 2 is a multiple of 6. Remember, they cannot be multiples of each other. And by the way, they also cannot have a they also, I didn't write this down, but I'm going to say this out loud in the video here. They cannot have a shared least common multiple with each other as well. They have to be completely unique. There has to be no multiplicity between them. So for example, we cannot use 6 and 8 because 6 and 8 share common multiples together. So if we were trying to use the proof of divisibility by 24, for example, there are other numbers we can use, but we cannot use 6 and 8. Wait, 6 times 8? No, sorry, that's 42. I'm silly. 42. 42. That's what I meant to say. I said 24. I was thinking about it backwards. 42. There are other numbers we can use for divisibility by 42, but we cannot use 6 and 8 because there are some numbers that are divisible by both 6 and 8 that are not divisible by 42. Most notably, the number 24. The number 24 is divisible by both 6 and 8, but obviously 24 is not divisible by 42. So that's something I didn't write down that I should have, but you have to keep track. And another example here, we have 25. 25 has only one multiple, and that is 5. That's 5 squared, obviously, equals 25. And that means we cannot use 5 for this rule. We're going to have to come up with our own special method for divisibility by 25, which I already did. I showed that earlier. Obviously, if the final two digits are either 25, 50, 75, or 0, it's divisible by 25. But the point of that is to show you cannot choose like a square, right? If you cannot have the same number as its multiples for proof of the least common multiple unique multiples method, they cannot be squares. They cannot be the same, and they cannot be multiples of each other, and they cannot have a least common multiple between them. Which, by the way, for the case of 6 and 8, what's the least common multiple? 2, right? Yeah, they both have a shared common multiple of 2. So that means, by the way, that by definition, one of the numbers has to be odd. because if both were even, then they would both have a shared common multiple of 2. So there is, however, another rule that does allow us to use these numbers, but I'll show that later in the document, and that requires division, and that breaks the rules of the document. So yeah, later in the document, I'm going to show kind of a rule that breaks this, but that is kind of like a separate thing. You don't need to know that. I'm just including it because I thought of it, and I don't want to exclude it from the document, and I'm going to talk about it. But that breaks the rules of this overall document, which is no division. So let's talk about let's talk about divisibility by 6. How do we know if a number is divisible by 6? If it's divisible by both 2 and 3. 2 and 3 are not divisible by each other, and they don't have any least common multiples, and they're obviously not the same number. So any number that is divisible by both 2 and 3 have to be, by definition, they have to also be divisible by 6. So simply all we need to do is prove that a number is divisible by 3, and if the number is even, then it's also divisible by 6. So for 7,488, for example, we add up all the digits to see if it's divisible by 3, and by adding up all the digits, we get 27. 27 is obviously divisible by 3, and it is indeed even because the final digit is 0, 2, 4, 6, or 8, and thus 7,488 is divisible by 6. Keep in mind when you're doing divisibility by 3, right? This number here, this sum, doesn't need to be divisible by 6. In fact, I'm pretty sure this number isn't divisible by 6. 27, no, it's not. But it doesn't matter. As long as it's divisible by both 3 and 2, it's divisible by 6. Divisibility by 12. Remember how I said we can't use 6 and 2 because they're divisible by each other? Well, thankfully, 12 is divisible by 2 other integers, 4 and 3. So, if we can prove that a number is divisible by both 4 and 3, then bada bing, bada boom, it's divisible by 12. So, with our example here, 7,488, we've already proved that it's divisible by 3. But is it also divisible by 4? Well, let's see. Multiplying out the numbers here, 0 times 1 gives us 8, and then 2 times b is 16, plus c times 8 is 0, plus d times 7 is 0, because again, we're multiplying these by 0. 8 plus 16 equals 24. 24 is, of course, divisible by 4. And since it is divisible by both 3 and 4, it has to be also divisible by 12 by definition. Because it's impossible to have a number that is both divisible by 3 and 4, but isn't divisible by 12. That is literally impossible. Next up, 15. So 15, again, we're going with the least common unique multiples, which are 5 and 3. If a number is divisible by both 5 and 3, it's divisible by 15. Divisibility by 3 again, add the integers together, so for 1350, adding them up we get 9, and the final digit is 0, and thus it is divisible by 15. 18. So, for divisibility by 18, we gotta prove if it's both divisible by 9 and 2. Let's take an example of 1638. Adding up all the numbers together, that gives us a number 18, which is of course divisible by 9, and it's even, so it is of course divisible by 2, and thus it's divisible by 18. And I put this in parentheses here. The sum doesn't have to be divisible by 18, right? In this specific example, it is, but it doesn't matter, right? If adding up the sum of the digits gave us 9 or gave us 27, that's totally fine, as long as it's divisible by 9, okay? It doesn't have to be divisible by 18 as well. And I showed that previously with the example of divisibility by 12. Alrighty. So, remember how on the very first slide I mentioned that these methods will allow us to find divisibility without division? Well, this is the first of only 2 methods that breaks that rule. So I could exclude it from the video because it's like, technically breaking the rules, but I want to include it because they're alternate methods, and they do require division, but it is substantially easier, okay? Because in my opinion, dividing bigger numbers by smaller numbers is a lot easier than dividing bigger numbers by even bigger numbers. So this will allow you to determine divisibility with significantly less division. So let's take an example, right? Let's say you want to know if a number is divisible by 12 and you don't want to use the method of 3 and 4, okay? Well, all you need to do is divide that number in half and then find out if that number is divisible by 6. This works because if the number when halved is not divisible by 6, then it can't possibly be divisible by 12, since dividing by 12 is the same as dividing by 2 and then dividing by 3. So, let's take, for example, 7,260. This is divisible by 12, but 7,266 is not divisible by 12. And this is important, right? You got to do it in a very specific order. Or you don't have to do it. You can do divisibility by 6 then 2, but in my opinion, dividing by 2 is a lot easier than dividing by 6. But what matters is that if you prove divisibility for one of the factors, that you can prove it for the other factor. So dividing this outright, I don't remember what the number is. I didn't put it in the document, but I know for a fact that when you divide this by 2, this number that you get is not divisible by 6. But if you divide this number by 2, the number that you get is divisible by 6, and thus this number is divisible by 12, and this number is not. And yeah, here's another example. Let's say you're trying to find out if a number is divisible by 49. The only number divisible by 49 is 7. And although there is a method that doesn't require division, which I'll show later on, um, if you want to, you can simply divide that number by 7, then find out if that number is still divisible by 7. So basically what that means is if you divide a number by 7 twice, then that means it's divisible by 49. Because, of course, there's no way that you can divide a number by 7 twice and it not be divisible by 49. That's impossible. So, yeah. Moving on to the next category. Now, we're going back into the original rules here where we're not using divisibility or anything like that. So this is back to the original rules. We have prime numbers above 5. Of course, we showed examples of divisibility by 2, and 3, and 5, and 9, and 18, and 32, and stuff. But there's a bunch of other numbers that I missed for good reason, because they're a lot more complicated. So, yeah, there's a couple of different methods that you could theoretically use. And one method requires one really difficult to remember calculation that might be repeated if you can't tell whether or not a number is divisible, and another requires a far easier to remember method, but must be done many, many times until you find a number that you know it is divisible by. So we're going to show the second method first because the first method is ungodly difficult to remember. So, divisibility by 7. Now this is the subtract by multiples method, okay? So, do you remember your 7 multiples? Well, to find out if a number is divisible by 7, simply subtract a multiple of 7 that would get the final digit to be 0, and then divide by 10. Then rinse and repeat. So, the multiples of 7 are 21, 42, 63, 14, 35, 56, 7, 28, and 49, and that is in order of the lowest to highest value of the final digit. So, look at this, right? 21, the final digit is 1. 42, final digit is 2. 63, the final digit is 3. 14, final digit is 4. You get the idea. But this is relevant because what you're going to end up doing is you're going to be subtracting. You're going to look at whatever your final digit is, and you're going to be subtracting by whatever this number is. And of course, if it's 0, you're just going to divide it by 10. But if it isn't 0, if it's any of these numbers here, then you're going to subtract any number that represents the same corresponding final digit. So for the number 11,340, we do this. We're going to take this number, 11,340, divide it by 10. We're left with 1,134. Then we're going to subtract 14 because 14 is divisible by 7. So now we're left with 1,120. We're going to divide that by 10 to give us 112. If you still don't know if 112 is divisible by 7 or not, well, we can subtract 42 so that we're removing the final digit to getting it to be 0. And look at that 70. 70 is obviously divisible by 7. It is 7 times 10. Bada bing, bada boom. By subtracting the multiples and dividing by 10, this allows us to get our number reduced down to a point where we can recognize it as being divisible. So this can be tedious, this can be taking quite a long time, and of course it can be quite difficult, especially if you have to do it off your top of the head and try and remember what numbers correspond with which final digit, but I think it's far easier than any of the other methods that have been proclaimed out there. There's one method where you have to multiply it by like 0.5 and all that stuff. And the thing is, multiplying by 0.5 is the same as dividing, and we don't allow dividing. We allow adding, subtracting, and multiplying, but not dividing in this here document, except for like the two rules where I said I'm going to allow it. Anyways, yeah, another note is you could do addition, right? You could theoretically add a multiple of your desired number if you think that's easier. So a good case to do it would be for specifically divisibility by 7. And let's say the number ends with 3. So let's take the number of 3,143, right? Using the previous method, you would have to subtract 63, divide by 10, subtract 28, divide by 10, and you're left with 28. That works, it's fine, but maybe a little bit more complicated. But, however, if you add 7, right? Because, again, as long as the final digit is 0, that's all that matters. And as long as you're either adding or subtracting by a multiple of 7, then you're not breaking any divisibility rules. So if you add 7, that'll give you 3,150. Then you divide by 10, get 315. And again, it would arguably easier to add 35, because I'm going to be honest, for me personally, when I'm subtracting a number and I have to start carrying stuff over and I have to keep track of what was in the primary place, that gets a little bit complicated, right? So we could subtract 35 here, but then I would have to be like, okay, 15, right? Okay, so what am I removing? 15, but I'm keeping 20, so I'd have to do 200, or I would have to do 300 minus 20, because then that would be the same as 315 minus, or that 315 minus 15, then minus 20, and minus 15 minus 20 is the same as minus 35. That's how my brain works. If you're like super smart and you can do that off the top of your head and it's super easy for you, good for you. But I would argue it's easier to just add 35. You don't have to worry about carrying over any numbers. You just add 5 and then you add 30. Bada bing, bada boom, 350. Divide by 10, you get 35. 35 is obviously divisible by 7 because that's what we just used. So in my opinion, that is easier. And sometimes I might use addition or subtraction, and you're going to see throughout this entire document, I'm going to basically arbitrarily decide whether I'm going to use addition or subtraction. It doesn't matter as long as you're adding or subtracting a number that gets the final digit to be 0, and it's divisible by the number that you're trying to find the divisibility for. So, divisibility by 11. The same principle applies, just subtract whichever multiple corresponds to making the final digit 0, which in this case is quite easy to remember since the multiples are simply the same digit twice. So 11, 22, 33, 44, 55, these are super duper easy to remember. I know somewhat off the top of my head my multiplication times tables up to 12 times 12. I still have to sometimes think about it. Like if somebody was like, what is 7 times 11? I'd be like, or not 7 times, bad example. What is 7 times 9? I'd have to think like, 64. You know what I mean? I'd have to think about it. 7 times 11? 77. Got it. Easy. Super easy. So, take the number 23,881, subtract by 11. That'll give us 23,870. Divide by 10, 2387. Subtract by 77, 2310. Divide by 10, 231. 231, final digit, get that to 0, so by subtracting 11, gives us 220. Divide by 10, 22. 22 is obviously divisible by 11, and thus this entire number here is divisible by 11. Now, there's actually a couple of other methods that I even have in this very document. There's 2 other methods that I show, but this is using the subtract divide by 10 method, right? Excuse me. And by the way, if I wanted to theoretically, I didn't want to, but if I wanted to theoretically for this point right here, I could have added a 33 instead and then done the math from there, but I didn't, of course. So at this point, you get the idea. You understand the whole dividing by 10 thing, so we're going to completely remove it, and we're going to replace that symbol with this square box here. So whenever you see this square box, that just means divide the previous number by 10, and then you'll see exactly what happens after that. So here are the multiples of 13 in order: 91, 52, 13, 104, 65, 26, 117, 78, and 39. So if we're trying to find out if 12,506 is divisible by 13, well, we can add 104. That'll give us 12,610. Dividing by 10 gives us 1261. We're going to add 39. That'll give us 1300. And look at that. Very easily, we can tell that 1300, if you divide by 10 twice, will give us 13. And 13 is obviously divisible by 13. So this is an instance where adding would probably be a lot easier than subtracting, because otherwise you would need to subtract 12,506 by 26, and then you get some weird number, and it wouldn't be as clean. This only required 3 steps, like super simple. Divisibility by 17. Again, we take the multiples 51, 102, 153, 34, 85, 136, 17, 68, 119, and then we subtract or add to get to the point where we have a number that is recognizably divisible by 17. Ideally, one of these numbers here. So for 41,252, subtract by 102, 41,650. Turn this into 4,165, subtract by 85 for 4080, add 102 for 510, that'll give us 51. Divisibility by 19. Again, more or less the same idea. 171, 152, yada yada yada. So if we have 112, 347, subtract 47, gives us this here, turns into this, subtract 19, gives us this, turns into this, add 19, gives us this, turns into this, and 114 is of course divisible by 19. So there we have it. I'm gonna kind of just showcase some examples here. I'm not gonna like thoroughly explain it because you get the idea at this point. But here are some examples. Here's an example of divisibility by 23. Here's an example of divisibility by 29. And of course, this one is interesting because it starts off immediately by dividing by 10. So that's why there's a box right here at the beginning and why it's reduced down to 18,000 immediately, because we immediately divided by 10. And divisibility by 31. This is a good example right here, right? Because we have 499,999. I would have no idea whether or not that's divisible by 31 just by looking at it. But we can add 31. That'll give us this number right here. Add 217, subtract 62, minus 186, 31. Boom. And then out of order here, because I kind of at this point was like, divisibility by 27. So we kind of skipped this at this point. Should probably be between 23 and 29, but whatever. It's fine, you get the idea. And these are the rest of the 20s that I didn't show earlier. So for divisibility by 21, you have to know if it's divisible by both 7 and 3. So I proved right here divisibility by 3, and I proved right here divisibility by 7. There's also the subtract then 10 method if you want to do that instead. Both of these methods work. Both of these methods work. So you can subtract by multiples of 21. So here we are right here. These are the multiples of 21, and we can just keep subtracting until we get to a number that we know for a fact is divisible by the number that we want to know. And in fact, you could do it a double method, right? You could start to do this and then get a number that you're like, okay, I'm not sure, and then switch to this method and see if that number is divisible by both 7 and 3. You could mix and match if you wanted to. Divisibility by 22, well, simply if the number is divisible by both 11 and 2. Of course, 11 is not a factor of 2, 11 is not the same number of 2 as 2, and 11 and 2 don't have any shared least common multiples. So there you go. For this example here, 11,000 or 187,110 divide by 10 gives us this number, minus 11 gives us this number, divide by 10 twice gives us 187, subtract by 77 gives us 110, divide by 10, 11. 24. So for 24, you cannot obviously use divisibility by both 6 and 4 because 6 and 4 have shared least common multiples. So you have to use 8 and 3 because 8 and 3 don't have any shared least common multiples. So if a number is divisible by both 8 and 3, that means it is divisible by 24. So proving right here divisibility by 8 by using the method I showed earlier, and proving right here divisibility by 3. Divisibility by 26, if it is divisible by both 2 and 13. So if the number is divisible by 13 and is even, it's divisible by 26. So here are the multiples of 13. Again, we're proving divisibility by 13 here. So we're going to keep subtracting until we get to the point. Ironically enough, we ended up using 26 twice here. So we add 26, give us this number, add 26, give us this number. Subtract by 13 gives us 390. 39, boom, we know it's divisible by 26 because this number is even and it's divisible by 13. And as I say right here, this number here obviously is not divisible by 26, but it doesn't matter because what matters is that it's divisible by 13 and it's even. So divisibility by 27 here again. Divisibility by 28. So I didn't even show an example because I'm just like, you get it at this point. I want to move on to more interesting stuff. So a number is divisible by 28 if it's divisible by both 7 and 4. So you now have the knowledge and the tools. So I'm going to stop going into specific examples because you get the idea, and I'm going to do a very brief overview to determine divisibility of any numbers between 30 and 50. So remember when I said I'm going to go like from numbers 1 to 20? That was, like I said, kind of going into more detail specifically. At this point, I'm just going to show you a chart. Here's the chart right here. Divisibility by 30, if it's divisible by both 10 and 3. Divisibility by 31, again, you have to do the add and subtract and divide by 10 method. Straightforward. 32, you have to use this interesting little formula here. Divisibility by 33, if it's divisible by both 11 and 3. Divisibility by 34, if it's divisible by both 17 and is even. 35, 7 and 5, 36, 9 and 4. You cannot use 6 and 6, obviously. You have to use 9 and 4. 37, you're going to have to use this method. 38, 19 and 2. 39, 13 and 3. 40, 10 and 4. Ooh, wait a minute. These share a least common multiple. Maybe that's not correct then. Because there are numbers that are divisible by both 10 and 4 that aren't divisible by 40. So that's actually incorrect. Oh my goodness, I didn't even think about this. Somehow didn't notice this until I was like working on this right now. Oh my goodness. What numbers are divisible by 40? Oh my god, I literally somehow didn't notice until just now. That's crazy. That's fine, I'll find something. 40 divided by, I don't know, 3? Nope. 4 is obviously 10. 5 is 8. 8 and 5. Yeah, 8 and 5. That's what it is. So if a number is divisible by both 8 and 5, then it has to be divisible by 40. 8 and 5 share no least common multiples. There is no number that is both divisible by 5 and 8 that isn't also divisible by 40. Is that correct? 5, 10, 15, 20, 25, 30, 35, 40. Yeah, that has to be correct. Yep. 41, hold on here. 41, doing the method because it's a prime number. 42, there's actually two methods that are both equally viable. You can either prove divisibility by 21 and if it's even, or you can prove divisibility by 6 and 7. Both equally work because neither of these have instances of one number being a factor of another number or having multiples within each other. As in, there's no shared least common multiple between 21 and 2, and the same with 6 and 7. And obviously, 6 and 7 and 21 and 2 are obviously not the same number, so bada bing, bada boom. 43, this method. 44, 11 and 4. 45, 9 and 5. 46, 23 and 2. 47, using the divisibility method. 48, divisibility by 16 and 3. And 49, you can do the original method. And a bonus method, which I'm really excited to show you guys. This bonus method is ridiculous. I don't even know if I'm going to go into it. How long have I been recording? An hour and 3 minutes. My goodness. We're on slide 55. This is 70 slides. This is ridiculous. I did not expect it to take this long. I'm really thirsty. Let me drink water. But I really want to get into this. This is really important. So, as I mentioned, divisibility by 49, you could do the original classic method everybody knows about, where you do the divide and then the divide method, then no, it's add or subtract, then divide by 10, right? And that's what this is right here. So, for example, 5,920 is that number divisible by 49. Arguably, um, the most straightforward way of finding out is by dividing by 10, giving us this number, subtracting by 392, giving us 4,900, dividing by 10 twice, 49. Obviously, 49 is divisible by 49. Boom, right? But more excitingly, I put so much effort into this, and I'm so excited to show you guys the difference from 50 method. And this is ridiculous because I spent a significant amount of time working on this theory, even though it's only for divisibility by one singular number. But of course, this is all about using your brain, right? So, 49 is only one away from a number that is rather easy to find if it's divisible by. 50 is obviously one of the easiest numbers to see if a number is divisible by 50 or not. If it ends with a 50 or ends with two zeros, it's divisible by 50. So because of this, we can try an interesting but super complex way to find divisibility by 49. It is also the other aforementioned that uses division. So this is the other method where you do need to use division. But it's only division by 100, so, or division by 50, whatever, right? So it's not that bad. So let's say we need to find out if a number is divisible by 49, and we're going to call that number x, right? We're trying to find out if x is divisible by 49. First off, we need to find the distance from that number to the next highest number that is divisible by 50, aka the next highest number that either ends with two zeros or 50. And we will call this next highest multiple of 50 the NHM. The NHM, next highest multiple. You see what I did there? So we're going to take a look at the difference between this x, which is our original number, and the next highest multiple of 50. And we're going to call this difference here delta. And see, we got to find out if NHM, if the next highest multiple, is divisible by delta. Okay? So this is important, right? If our next highest multiple is divisible by 50, which by definition it has to be, and it is divisible by delta, then we know that x is divisible by 49. This is, of course, only a one-way thing. This is only a way to prove that it is divisible. This isn't a way to prove that it isn't divisible. And the reason why is because when you get to numbers past 49, this method doesn't work. So let me read further, okay? So this method, this simplified version of this method, only works for numbers less than 2,401, aka 49 times 49. And the reason why is because above that point, the distance to a number divisible by 50 might not be delta times 50, even though it could be divisible by 49. So if all of this was confusing, let me show you an example here, okay? So let's take a number 1,764, okay? 1,764, the next closest number that is divisible by 50 is 1,800. So let's take a look at that difference. Is the difference between 1,800 and 1,764 is 36. So now we need to find out if 1,800 is divisible by 36. So we can divide by 50. And what I like to do, by the way, because for me, for whatever reason, I'm dumb and I can't really do divide by 50 easily. So what I'd like to do is divide by 2 and then divide by 100. So I multiply this by 2, giving us 3,600, and then divide by 100, giving us 36. Because for whatever reason, divide by 50, my brain just collapses. But times 2, divide by 100, easy peasy, right? So this means that 1,800 is 36 times 50. That is what it means. It's divisible by 50, and it is divisible by 36, because that's what we just proved, obviously, right? We proved that it is 1,800 divided by 50 is 36. That's literally what we just did. So what we know is that 36 times 50 is 1,800. And this means that by taking 36 away, right? 36 times 50 is 50 instances of 36. If we take away one of those 36s, that means that we are left with 49 instances of 36. And that's what we got as the original number. You see why this works? You see how cool it is, right? So because we got to this point right here, which is 1,800, right? And we got to this point by doing 36 times 50, by taking away 36, turning it into 36 times 49, if we get the original number, that means that this is divisible by 49. Isn't that cool? Okay, so here's another example. 1323, the next highest number that's divisible by 50 is 1350. So 1350 right here, we got to figure out what number. This is always divisible by 50, but we got to figure out what number it is. 1350 times 2 divided by 50 is 27. So is that the difference? It is. 27 is the difference between 1323 and 1350, and 1350 divided by 50 is 27. So that must mean that 27 times 49 is 1323, because this is 27 times 50 is 1350. So by taking away one instance of 27, that'll give us 1323. And that is 27 times 49, and obviously in that case it's divisible by 49. The reason why this works should be obvious, and it's because if delta times 50 does not equal x plus delta, then x plus delta minus delta cannot be divisible by 49. So to show an example, right? Delta times 50 would be 1800, for example, right? And if x plus delta, which is also the same as 1800, right? So if 36 times 50 does not equal our original number plus the difference, which is 36, then the original number plus that number minus that difference cannot be divisible by 49. That should make sense to you if you have a math brain. It might be confusing the way I'm wording it, but this is, by definition, delta is our next highest multiple minus our x. That's what delta is. So if this number multiplied by 50 does not equal the difference, which this right here is the original number plus the difference, then obviously, when we remove that difference, we're not going to originally get x. So why does this not work above 2,450? Well, the reason why is because 51 and above are going to give us with a next divisible number, which are distances that do not allow us to comprehend this kind of math. This original method doesn't work, okay? So let's take, for example, 49 times 51. So this is 2,499. The next the next number that is divisible by 50 is 2,500. And that gives us a distance of 1. 1 is the distance. I think you can start to see the problem here. 2,500 divided by 50 does not equal 1, which theoretically would say that this means that this 2,499 is not divisible by 49. But of course, we know it's divisible by 49. As I said, this is 49 times 51. So you might be wondering, okay, why is this the case? Well, it's because the closest relevant number is greater than our maximum searchable number. In other words, we would not need to look for the next distance to the next possible number divisible by 50, but for the number after that. So if we knew how much further ahead we needed to look, this wouldn't be a problem. But because we are with our original method, we were going just for the next number, you can kind of see why this kind of leaves us stuck here. However, the strategy can still be salvaged. I mean, there's no easy way to word this, because this is a complicated method, but basically, if you divide the next highest multiple by 50, and it isn't the difference, then you'll have to do this complicated series of steps, okay? This is a little complicated, but check this out, right, okay? Look at the number that you did get when you did our next highest multiple divided by 50, okay? We're going to call this OD for the original divisor. So if you subtract 50 from that by as many number of times as it takes to get you to 50, so we're going to call this r for the remainder. Then we're going to count how many times you had to do this subtraction of 50. We're going to call this sigma, okay? And if sigma, which is, again, the amount of times you had to do the subtraction, plus our remainder equals delta, then x is in fact divisible by 49. Is this complicated? Yes. Let me show you an example, so hopefully it'll be less complicated. So let's take the number 10,535, okay? The next closest number that's divisible by 50 is 10,550, okay? What is the difference? The difference is 15. This is not x. I don't know why I wrote this as x. This was supposed to be delta. I'm sorry. Ignore that. Here, let me rewrite it. This is supposed to be delta. Oh, I gotta switch to this keyboard. Delta. So, our difference is delta. And if we divide 10,550 by 50, that gives us 211. And obviously 211 does not equal 15. Duh. So, what do? Are we stuck? No. We're going to subtract 50 from 211 a total of 4 times. And why are we subtracting it by 4 times? It's because that is the minimum number of times that we can subtract it to get this number to be less than 50 but greater than 0. So, in this case, we're going to be left with 11 because we're subtracting it by 200, right? 211 minus 200 is 11. And again, 50 times 4 is 200. So that's where we're going to get it from. But we're going to keep track of the sigma here, okay? We're keeping track of all of these numbers. So we're going to have to keep track of the sigma. We're going to have to keep track of the remainder. And look at this, right? 11 plus 4 equals 15. And thus 10,535 is divisible by 49. Did I convince you? Well, maybe not, but how do we know? How do we know that this works, okay? Well, let's do some logic here, right? Let's take the original number, 10,535, and what was the number that we subtracted it by? 200, okay? Let's add 200 then. And then we do the exact same previous method. So we're going to have 200, that's going to leave us with 10,735. Our next closest multiple is now 10,750. So we're going to add 15 again. Now, if we divide by 50, that'll give us 215, and look at that! 215 is simply our original remainder, or our original delta, plus 200. Pretty genius, huh? Pretty genius. So, going back to the original example, we can see that 2,499 is divisible by 49. How do we do this? Well, let's add 1 again. We're going to add 1, okay? So that is going to give us 2,500. 2,500 divided by 50 is 50, okay? Obviously 50 is not 1. Duh, okay? So our difference here, our delta, is not the same as our remainder, okay? So we're going to subtract 50 from 50 to get us to 0. Now we're going to keep in mind that we subtracted 1 time, okay? So we're at 0, we're at a number that's less than 50, but greater than, or isn't negative, basically. It could be 0, that's fine, but as long as it's not negative. So how many times do we have to subtract 50 from 50? Once. So we subtracted 1 instance of 50. Then we're going to go ahead and add 1 as our sigma, okay? Because that's how many times we subtracted, okay? The amount of times we subtracted 50 is 1 time. So we're going to add the amount of times we subtracted to our value, to our remainder, which is 0. So 1, which is our sigma, plus r, which is our remainder of 0, is delta, which is 1. So look at that. Remember how we originally got a difference of 1? Well, if we take a look at our sigma, which is 1, the amount of times we subtracted by 50, and we add that to a remainder of 0, because when we subtracted 50 by 50, that gave us 0, that in fact gives us delta, which is 1. That's really cool, isn't it? Like, that's really, really cool. So this method isn't perfect, unfortunately, and I'll explain in a moment why. But first, let's show some examples, because maybe that still didn't convince you that this method is foolproof. And you should be convinced, because the method isn't foolproof, and I'll show you why, but it still does work within the realm what we're looking at, right? So 4,214. So now we have our number of x, 4,214. Our next highest multiple is 4,250, which is our next highest multiple of 50. And to get to that value, we have to add 36. So now we have our x, our delta, and our NHM. So our NHM, 4,250, we're going to divide it by 50 and see what we get. In this case, we get 85. Again, dividing by 50, in my opinion, is not bad, not easy at all. I think that dividing by 50 is significantly easier than dividing by 49, okay? So dividing by 50, again, you literally just multiply by 100 and then, or sorry, multiply by 2 and divide by 100. It's super simple. Whereas dividing by 50, or sorry, dividing by 49 is needlessly complicated. So, again, for 4,250 divided by 50, if you really are like, I don't know what that is, simply just multiply this by 2 to get you 8,500. Again, this should be relatively easy to multiply by 2. You can see that 25 plus 25 is going to give you 500, or sorry, 250 plus 250 is going to give you 500. 4,000 plus 4,000 is going to give you 8,000. So this will give you 8,500, and then divide that by 100, that'll give you 85. So now 85 is our original divisor. Keyword original divisor. Keyword original is what I said. So now we're going to subtract 85, our original divisor, by as many times as it takes to get to a number that is between 0 and 49. So in this case, we only need to subtract once. 85 minus 50 times 1 sigma, because that's the amount of times we subtracted, is going to give us 35. So 35 is our remainder. And look at that. Sigma plus r does indeed equal delta. 1, which is our sigma, the amount of times that we subtracted 50, plus 35, which is our remainder after we did the subtraction, equals the delta, which is 36. Remember, we originally added 36 to this value to get 4,250 in the first place. So because that is the case, that goes back to our original logic that proves that this value is simply just this value minus 85, or minus one instance of 85, I guess, is what it is, right? Or rather, that it's minus, subtracting by 36 is this number, but another iterative example of that number, which in this case, I guess, would be 85, which would turn into 86. And we would subtract 86, because that would be another instance of 86. So we would subtract that 86, but that's the same as subtracting it by 50 and then subtracting it by 36. And that's why we are able to prove that. Another example, 12,838. X is going to be that. 12 is the delta, which gives us the 12,850, because 838 plus 12 equals 850. So this is our next highest multiple of 50. Again, we're going to divide by 50, which is 257. Again, shouldn't be too complicated to do this off the top of your head. You simply multiply this by 2, which will give us... Originally, it will give you... This will be 24, and then you're going to have to carry a 1 here. And then this is going to... Well, let me think about it, right? 85 plus 85 is... 170, right? 170. 85 plus 85 is 170. So 850 plus 850 is 1,700. Okay? So 1,700 plus 24,000 is going to be 25,700. And indeed, that's what we got right here. By eventually dividing that by 100, that'll give us 257. Again, I think that's a lot easier to do, which is why I'm okay with showing this method, because yes, we are dividing, which is cheating. You're dividing by 50 or dividing by 100, depending on what method you use, in which case, it's really easy. So 257 minus, how many instances of 50 do we need to remove to get the number to be between 0 and 50, or 0 and 49 rather? Well, 5 times 50 is 250, and that is going to get us 7, which 7 is indeed between 0 and 49. So we have 5 instances of 50 that we're going to remove. We're going to have a remainder of 7. So sigma plus r equals delta, right? 5, which is our sigma, plus 7, which is our remainder, equals 12, and indeed 12 is the delta. Really, really cool. Like, I am like, when I found this out, when I created this method, because I created this method, by the way, I was super hype. I was like, oh my god, this is super cool. So, here's the problem, right? That doesn't always work. Everything I just showed you doesn't always work. And the problem arises when your delta is less than your sigma. So if your delta is less than your sigma, all of a sudden you aren't able to subtract enough instances of 50 to get the sigma plus r to equal delta. In fact, it equals the overflow of that amount. So basically, whatever that number is subtracted by 50, that is what you're going to get. And again, the reason why this comes about is because when you're subtracting the amounts of 50, if the amount of times that you're subtracting it is not enough to compensate for the amount that you're subtracting by, that's when you're going to get into some problems. But that's okay, there's no problem. If you notice that your difference is less than the amount of instances of 50 that you're removing by, aka if you realize that your delta is less than your sigma, aka you're subtracting more instances of 50 than the difference, simply remove another instance of 50 and you get a negative number. And that totally works because all you need to do is continue what we were doing, add sigma plus r, which in this case is essentially doing sigma minus the absolute value of r, and you will get the correct delta. So here's a couple of examples. 17,199 plus 1, which is our delta, 17,200. Well, obviously, 17, well, first, before we do anything, first we're going to have to divide by 50, which is our NHM. We're going to have to divide this by 50, and that'll give us 344. Okay, obviously 344 is the amount of times we would have to subtract 50 in order to get to a number that's less than 50 is obviously way more than once. We're going to be doing that way more than one time. So instead, we're going to have to add the amount of times that we're going to subtract by 50 to the point where it's a negative number, okay? So we're going to get to our original value. So in this case, originally what we would do is 344 minus 50 times 6 sigma, and that'll give us 44. 44 is in between 0 and 49. However, again, going back to it, we realize, oh no, our delta is less than our sigma. We're going to have to subtract one more instance of 50 so that we get a negative number. So now it's at negative 6 is our remainder. And this allows it to be consistent because now sigma plus the remainder equals delta. 7, which is the amount of instances of 50 we removed, that gave us from, because originally it was 300, we're removing 350 from this, right? So this will give us negative 6. So 7 times negative 6, right? 7 times sigma, right? 7 instances of sigma. Negative 6 is our remainder. 7 plus negative 6 equals 1. Not convinced? Here's another example. 12,348. 12,348 plus 2 gives us 12,350, which is the next highest multiple. 12,350 divided by 50 is 247. Obviously, to get this number to be between 0 and 50 or 0 and 49, we're going to have to do more than 2 instances of subtracting by 50. So we're going to add 1 to whatever we were originally going to do. So 247 minus 50 times 5, which is 250, so this is 247 minus 250, will give us negative 3. And that's okay, because sigma, the amount of times we're doing it, plus the remainder, which is negative 3, equals delta, which is 2. So 5 plus negative 3 equals 2. This is super cool. This is super really, really cool. Oh boy, and again, this was all just for divisibility by 49. This is ridiculous. I spent like who knows how much time on just this, but it's just such a cool method that I had to include it. Oh my god, I forgot about the cycles. I thought we were done. I gotta go. I can't give up now. How long the recording be going? An hour and 20 minutes. We gotta go. Oh, it's only 5 more slides. We're chilling. We're chilling. So remember, like way back when I said there's 2 methods for finding out numbers that are prime numbers? This is the other method, okay? So for cycles, we got the easy stuff, right? we're going to now have to take into consideration again, once again, we're going to have to take into consideration every single digit, which is what I said earlier, okay? But this is going to go in cycles, which means that we're going to have to keep. It's kind of like the original method. Remember the original method where we took into consideration A, B, and C, and D, and stuff like that, right? We kind of ignored that for the other method, right? But we're going back to this method with the A, B, C, D, and E, and we're doing the multiples and stuff like that. But we're going to multiply by very specific multiples, okay? But they go in cycles indefinitely. So rather than there being a clear formula that I can show you, instead I can only show you the cycle and then say you continue this cycle for however many digits you have. If your digit is like 17 digits long, or if your number is 17 digits long, you just continue the cycle as many times until you end. So these require a continuous cycle. So for the cycle of GFEDCBA divided by 7, the cycle is 1, this is a spoiler alert, but I'll say it anyways. The cycle is 1, then 3, then 2, then 6, then 4, then 5, then 1, right? And let's say you had a number that was 10 times larger than that, then you would go to 3. If it's 100 times larger than that, you go to 2, and you just keep going in the cycle. The cycle goes 1, 3, 2, 6, 4, 5, 1. So, and I said right here, if you need to find a number larger than 9,999,999, then the tens million place will be multiplied by 3, the 100 millionth place will be multiplied by 2, the 1 billionth place will be multiplied by 6, the 10 billionth place will be multiplied by 4, and so on. You get it. So, I kind of gave it away, but here we go. This is the continuous cycle method. So, how do we figure out whether or not a number is divisible by 7? Well, this is one way to do it that doesn't require division. A plus 3b plus 2c plus 6d plus 4e plus 5f plus g, and then that continues on, right? So for g, what's after g? A, B, C, D, E, F, G, H. H would be 3h. I would be 2i. J would be 6j, and so on and so forth. So, and this is why it works, right? This is why it works. A plus 10b plus 100c plus 1000d plus 10,000e, blah, 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 blah. If we're going to split that out, that'll give us A plus, we're going to remove 7, 3b, we're going to move 2, 2c, we're going to remove 4, 4e, we're going to move 5, and we're going to remove 1. And now all of a sudden, 98, that's divisible by 7. 994, that's divisible by 7. 9,996, divisible by 7. 99,995, divisible by 7. Then we go back to 1, divisible by 7, or 1 minus a million, divisible by 7. Okay, cool. So let's take a number. Because, I mean, it's one thing to just say something, but let's prove it. 1,760,402. We're going to multiply 1, or a by 1, so this is going to give us 2. We're going to multiply b by 3, but it's still 0 in this case. We're going to multiply c by 2. We're going to multiply d by 6. We're going to multiply e by 4. We're going to multiply f by 5, and g by 1. So 2 plus 0 plus 8 plus 0 plus 24 plus 35 plus 1, oops, equals 70. And 70 is, of course, divisible by 7. And this method works. Again, if this was, let's say that it was, how would I, ooh, you wouldn't really be able to do it in an easy way, but 3 plus 2, is there any multiples of 3 and 2 that'll give us the 7? Oh, let's say that, this was, let's add a 3 at the front, right? And let's add a 2 after that. So 3 and then 2. Let me double check. I'm pulling this out of nowhere. I have no idea if this is true. First off, let's prove that this number here is indeed divisible by 7. So 1,760,402 divisible by 7. And indeed, there it is right there. So, again, I'm kind of trying to prove my own method here. Let's add another couple decimals to get this to be 77. So we're going to say theoretically that it's uh 3 and 2. So 321 million, this number. So 321. This should work. No, maybe I did it the wrong way. No, it's 230. Sorry. 230. So 231,760,402 divisible by 7. Please work. Oh, it didn't work. No, why didn't it work? Oh, because it is the other way around. Because I was multiplying the 3. Oh, yeah. Okay, so I did do it. I did have it right originally. My bad, I'm tripping. 321,760,402 divided by 7. Okay, why did that not work? Did I type it in wrong? That should have worked, according to my own math. Because 3... Oh! I'm stupid. It's because I'm multiplying it for no reason. I'm multiplying for no reason. Right. So times 7, that gives us that. So then we subtract, because this would have to be this b here, which is our next value after that. That would have to be 1. So we have to subtract by 10 million. Then divide by 7. Okay, it still didn't work. 2 times 3. Oh, I see. This is one number too large. So I have to subtract by 100 million. This is the number I should be. Yeah, there we go. Hey. All right, so hopefully you can see why that works. 211 million. 760,000. I'm struggling here. 402. And the reason why this works is because all we're doing is adding, one instance of 3 and 2 instances of 2, and of course 3 plus 4 is 7, so this total number would turn into 77. But of course 77 is divisible by 7, so it works out. There we go. Sorry, I kept messing it up, but I got it, and I'm super proud of myself. That was clutch. That was completely unscripted, unrecorded. I had no plans of doing this. I really wanted to prove that my method works, and that's how you prove it, I guess, right? By potentially embarrassing yourself. But yeah, there we go. So, divisibility by 11. This is method number 1. Going kind of keeping on track with the original thing right here, right? So, again, we're trying to prove whether or not this sum here is divisible by 11. So, we can start off with doing a minus b plus c plus 10d plus e. We kind of alternate between plus 10d plus e because this is going to be right here, right? Look at this, right? So 0a plus 11b, 11b minus b equals 10b, plus 99c plus 990d, subtract d. This is divisible by 11. This is in fact 11 times... What is this? 11 times 90? I guess? 11 times 90? I think that's correct. Yeah. And then this is divisible by 11. So you go back and forth. After this point, you go back and forth between adding multiples of 10 and just adding 1. So again, this is method number 1, okay? So for 38,786, got 6 minus 8. So 6 minus 8 plus 7 plus 80 plus 3. This gives us 88. And the cycle starts at the 100 digits because obviously 10 does not go into 11. However, this is the alternate method. This is obviously way easier. This is probably what you're immediately thinking when you saw it. And then you simply just subtract every other number. So, in this case, we do 2 minus 8 plus 7 minus 2 plus 3 minus 2. 2 minus 7 plus 2 minus 8 plus 7 minus 2 plus 3 minus 2 is 0. So the purpose of this is you're trying to get the value to be 0, okay? You want it to be 0. You don't want it to be any number that's divisible by 11. You want it to be exactly 0. So this is why this is an alternate method, because rather than proving that your sum is divisible by 11, you're trying to prove that it's exactly 0. So, yeah, 642,686. And for the original method, it's worth keeping in mind for the original method here, if if you only have like 2 digits here, then it's very possible you could get a 0, and I just kind of have to accept that because there's nothing you can really do about it. For example, if your number is 22, 2 minus 2 is obviously going to be 0. But presumably you're not going to really be worrying about that, because you should be able to know if a number up to 99 is divisible by 11, because it's literally if the number is repeated twice. Like, come on now. Alrighty, so now, divisibility by 13. Again, this is a complicated way of doing it. We have the cycle here of A plus 10B plus 9C minus D plus 3E plus 4F plus G plus H plus 10H plus 9I. This is where the cycle continues after this point. So as you can see here, we're going a coefficient of 1, a coefficient of 10, a coefficient of 9, coefficient of 1, coefficient of 10, coefficient of 9. So the cycle technically ends at this point here, but I continued to go on a little bit further just to kind of show you. So, and here's an example. 60,493,814. So we're going to add 4, add 10, add 72, subtract 3, add 27, add 16, add 0, add 6, add 60, add 9, and look at that, that gives us 195. And if you don't know that 195 is divisible by 13, again, you can kind of continue the method here. You can do 5 plus 90 plus... What would that be? Hold on, wait. 5 plus 90 is 95 plus 9. 95 plus 9, which is 104. And then I guess you could continue that method even further. 104, you have a 4 at the end, so 4 plus 0 plus 9 times this digit here, which would be 1. So this would be 9 plus 4, which is 13. Boom. So yeah, this method works. And that's the end. That's it. That's the rest of the document, because the rest of the stuff is either out of date or, I included it and I left it in here because because I want to, right? The rest of it I will show you, but I'm not going to go into any detail in any kind of capacity. I'm just going to show it just because it's like, this is what the slides used to be, and maybe I'll make slight adjustments. But yeah, so this is what I originally was going to do for divisibility by 17. I kind of gave up on it. As you can see, it goes all the way to U, because there's a lot of different... The cycle lasts a really, really, really long time. And originally, this was going to be the cycle here. We're going to have 1, 10, 15, 14, 4, 6, 9, 5, 16, 7, 2, 3, 13, 11, 8, 12, and 1. And then again, it continues like 10, 15, 14, 4. I'm assuming you get it. And then this would be the reason why here, because you add these numbers together. These numbers are all here. All of these numbers here are divisible by 17, and these numbers here are what you have to prove. And then here's an example, which is one of the most ridiculous examples I've ever seen. What is this even? 5 quadrillion? This is million, billion, trillion, quadrillion. Didn't even commit. And I just wrote down extra stuff because I'm like, ugh. As you can see, I kind of fell apart and I gave up. And I'm like, I'm not even going to show this. And this is some throwaway text and more throwaway text because I changed the way the document works. And that's it. That is the end of the presentation. I hope you guys enjoyed this 1 hour and 43-minute long adventure. This was crazy, but this was really fun. My throat hurts. I need to drink. It is 10:27 p.m. I need to drink something. I hope you guys enjoyed. Take care, peace, and bye-bye.